Hi everyone, I'm Jiaqi, and thanks for the introduction. So today I'm going to introduce Sirius. So how we Alibaba compose this network function chains into our own P4-capable edge gateways. So programmable switches are widely deployed in Alibaba Edge clouds. So in the Edge cloud, we host programmable switches along with several servers so that the client's requests no longer have to go to the central data center, and they can be directly served in the nearest edge cloud. So this improves the performance and also the reliability. So currently, the programmable devices are deployed in our thousands of edge sites serving global end users. So within the edge cloud, we're hosting a diverse set of network functions, including CDN, cloud gaming, DNS, and web caches. So here is a simplified chart of all the network functions we deploy in the programmable switch. So we are actually using, I would say, nearly all the advanced features provided by the programmable switches. For example, here we are using recirculation. We are sending the packet to the CPU to host, to incorporate, to use the memories in the CPU. We're using stateful operators that is supported in the ASIC. So our largest P4 program actually has 16,000 lines of P4 code. It has 248 tables, and it's occupying all 4 pipelines. So why this program is really complex? So the reason is, in the Edge cloud side, we need a dedicated network function chain for each traffic type. So here is a simple example. On the right side, we have the topology of our Edge cloud, and we want to implement a really, really simple NAT function in the Edge. So actually, that NAT function translates to 3 different network functions. So for example, if we want to, the VMs within the Edge cloud want to talk with each other, we have to build a VM to VM network function, which, for example, includes 3 sub-functions. So the first one checks the integrity of the packet. The second one does VXLAN checking, and after the checking, we'll route the packet to its correct destination. So as the main function of the NAT, it maps the external IP to the internal one, and so we call that traffic as an SNAT in traffic. So we need 5 functions to achieve the goal. So first one, similarly, we need a checker to check the packet, and then we need ACL to make sure we don't want any malicious traffic going in. And then we go to the core NAT table to translate the IP address, and then do the similar VXLAN and routing. When the packet wants to go out, because the inside server also has to reply to the outside, we are calling the traffic SNAT out. And it visits similar functions, but in a different order. So because the packet goes to belongs to the intranet, we have to first visit the VXLAN packet, and then do the NAT, and then do the ACL to go out. So in here, a really, really simple example, it requires 3 network function chains. And in reality, we have 10 such network function chains deployed on a single gateway. So, and on the table, the y-axis is the length of the table dependency. So we can see that not only do we have a lot of network function chains, but each of them is also quite long. So it has at least 10 tables depending on each other, and in the largest one, we have 26. So this is the reason why the network function or the P4 programs deployed on our Edge gateway is really, really complex. So during the deployment, we found out that our developers are really struggling to develop, debug, or even maintain such a program. So the fundamental reason we found is that there is a gap between the abstractions that the operator are developing and the real hardware that runs the program. So on the left, we have the similar network functions and the topology that the Edge cloud has. On the right, we're seeing 2 devices. So the top one is the programmable ASIC, and the bottom one is the CPU. So the programmer has to code the left side's business requirement onto the right side programmable target. So there are 3 gaps that we found are critical. So one is on the left, we have multiple network function chains. But on the right, we only have 1 pipeline. So the operator has to merge all of them manually. The second gap is because of the hardware limitations, we often have to use a lot of sophisticated features such as recirculation to implement or to host our complex network functions. But when people are writing P4 programs, all the recirculations are written in one pass. So the third mismatch is we actually are deployed on a single gateway, but because of the hardware limitations again, so the program has to be split and partitioned across ASIC and CPU. So currently the developer has to do it manually. So as a result, great efforts are spent on analyzing the mapping between these two abstractions, and the efforts the engineers spend is in proportional to the complexity of our gateway deployment. So here we propose Sirius that serves network function chain as abstraction rather than the traditional P4 pipeline abstraction. So the input of Sirius is first the NF chain definition, and second is the edge gateway's topology and traffic metadata. So by taking these two inputs, Sirius is able to synthesize a P4 program that runs on CPU and the ASIC separately. So here, so the naive solution, people would believe that there is a lot of overlapping or reuse network function modules across all the three chains. Then why not we just duplicate them and merge them in a pipeline way? So the upper part is a simple naive solution. We tried that, but it didn't work because we so the chart shows is the memory overlap across all the chains if we just duplicate them in the programmable ASIC. We found that duplicating the network functions and force it into a pipeline results in 3 to 5 times memory overhead and is way beyond the ASIC's resource capability. So as a result, we have to reuse all the network functions and without any duplication. And this is the source of all the trouble. So this is a enlarged figure of the 3 network functions that we just introduced. And it shows all the problems we are going to face and we are going to solve. So the first one is see that there is a loop in this network function chain. That in one network function, it first visits a NAT function, then goes to the ACL. But in the other one, it first goes to ACL and then go to NAT. So as we know that P4 programs are written in a pipeline way that does not allow such kind of loop exist. So first we need to pipeline this network function graph. So the second one is, since this is a merged graph, different packets are going to traverse different paths. So one packet may first go to a checker and go to the VXLAN. The other one may need to go to the ACL. But from the programming abstraction, we never know, because those are separately defined network function chains, we don't know how to identify the packet. Therefore, we need to identify the packet ourselves. Third one is, after we solve the first 2 problems, the memory consumption may still exceed the hardware's capability. Therefore, we need to partition the network function graph to so that the ASIC has enough resource. So how does Sirius solve this problem? So on the left, we have the 2 inputs, and Sirius proposed 3 solutions to solve the 3 challenges separately. So first one is traffic identification. Sirius, given the traffic information, Sirius can automatically generate a set of traffic identification tables to tag each packet, and so that then the synthesis program can apply the correct network function in sequence. So the key to this generation problem is to generate identification tables that minimizes the memory overhead. The second one is, given the graph where Sirius proposes several pipelining candidates, and each of the candidates is aligned with the hardware constraint. For example, it is from the left to the right, there will be no recirculation going back. So the second one, the goal of the second step is to propose plans that satisfy the throughput target, as we're going to introduce next. So the third one is given each pipeline candidate, Sirius will propose a partitioning plan that assigns a minimized number of network functions to the CPU so that the performance impact is minimized. So here, the goal is to fit the resource constraint. So due to the time limitation, so after the partition result is complete, Sirius will then call a synthesizer to translate the programs assigned to the ASIC to a P4 program running on the switch, and then keep the rest program running on the CPU. So due to the time limitation, I'm going to introduce the latter two solutions. So if people are interested, please refer to our paper or just email me. So when finding pipelining candidates, so it's not going to be a really huge issue. We just put them in order, and then we are going to check. So the problem with that approach is different pipelining solutions will have different performance overhead. So for example, if we just order the 5 network functions in this way, and we examine the 3 network function chains and see how they traverse through these 5 functions. So we're going to see that there are 2 highlighted arrows that are going backwards. So that to achieve those, we have to recirculate the packet after it traverses all of the switch and going back. So that means 2 such arrows actually means a 4 times throughput job for that specific traffic. So that means SNAT in traffic has 4 times less the potential capacity of all the other 2 network functions. So a better way might be we just reorder the NAT function and ACL function. So in here, we can see that only the SNAT out traffic and the SNAT in traffic each of them has 1 recirculation. So that means we have both of the traffic has 2x performance drop rather than the previous one, 4x. So another way to put it may be to just reorder the NAT table and VXLAN table. So similarly, will cause 2 times the performance drop. So this actually, so none of this candidate is bad unless we know the traffic requirement. So suppose the traffic we have to is 1/3 of the switch's capacity. So that means the first plan is not possible. We have to choose of the second 2. So then goes to the next stage. We want to partition the plan. So if you so in many of the cases, the network functions are way exceed the programmable ASIC's memory capacity. We have to assign some of them to the CPU. So in here, after pipelining, assigning, we still have one thing to take care of is that if we just randomly assign one network function to the CPU, it will cause another recirculation. Because on the bottom, we can see that the CPU is not directly connecting to the network. So any traffic going to the CPU will go to the switch again. That requires another recirculation. So in here, if we just randomly assign the routing network function to the CPU, so all the first 3 steps are as expected, but the last step will introduce an undesired additional recirculation. So that actually violates our throughput target. So a better solution would be we just put the NAT function in. So when the recirculation going from NAT to the ACL, it is naturally achieved by sending traffic from CPU to the ASIC. So we also solved another problem in the partitioning stage is that we have to encode recirculation into resource constraint. So we solve it by mapping a physical stage to logical stages. Again, due to time limitation, I'm not going to introduce it here, but please refer to our paper for detail. So as an evaluation, we are going to demonstrate the network function, the compensation process we do in our real program. So on the left, we have a network function chain. We just merged them by the order, and it actually results in 127 loops in merely 10 network function chains. So we Sirius quickly find a pipelining plan by introducing 2 recirculations. And as expected, this exceeds the memory capacity of the ASIC, and then it proposed a pipelining solution after assigning several tables into the CPU. So this whole process is done in minutes, while our most experienced developers will take weeks to propose such a similar plan. So as a conclusion, in production environment, we found that the abstraction gap between the business requirement and the programmable switch. Sirius solved this problem by proposing network function chain as an abstraction rather than traditional table-based P4 abstractions. Sirius automated network function chain composition in Alibaba's gateway and improved the development efficiency by 3 orders of magnitude. And that's all my talk. Thanks for listening.